So maybe I give you a more general idea, and then almost many of the slides have been taken by from Matthias and his team. So maybe I don't acknowledge in all slides. So this is the typical cardiac MR examinations, at least how we do it in Lausanne. So we start with some localizers, the cine to do the function. We inject contrast agent, there is perfusion, some wait time to let the contrast agent deposit in case there is scar tissue, and then to the late gadolinium enhancement. And Matthias once asked a technician, Jean-Baptiste, to figure out how many clicks he makes for a brain scan versus a cardiac scan. And it's about 10 versus, if you guess, something like 350, meaning that cardiac MR is not the simplest technique so far. And as an example, I would take coronary MRI to show you how complex this could become. So first of all, you have to trigger your acquisition, as we saw yesterday from Hood. So you have to take care of cardiac motion, and then you're gonna acquire the data always at a resting phase of the heart. Then the acquisition itself has several modules that one has to set up. So some contrast preparation like a T2 prep. Then there is a navigator to monitor the respiratory motion, and then the data acquisition. And then for some reason, this GIF plays like that in all slides. Basically, you monitor the position of the diaphragm and then just acquire some of the lines that are in the same respiratory position. And as you can imagine, this has a lot of user interactions. You have to set the trigger delay to make sure the ECG is correct, and to set the field of view, to set the field of view of the navigator, to set the acceptance window of the navigator, and so forth. So just to start the scan, you need a lot of expertise and a lot of clicks. And basically, this scan is complex. You have to localize where the coronaries are. You have to place the navigator, figure out the resting phase on a cine image, and then set the acceptance window. It's inefficient because the scan time is unpredictable. You only acquire very few data points during the acquisition. Then there is no motion management. You just try to get consistent data, and it's prone to failure. And then it's very application specific. So you choose one contrast, and that's it for that acquisition. And what you would want instead is a wider field of view. So if you accept more data, then you care less about how big is your field of view. So you try to acquire a bigger field of view, no navigators to place, a continuous acquisition, so no ECG to take care of, and then an exam that could start with a simple click with a fixed scan time, so not depending on the respiratory pattern, an acquisition that is continuous, so that you use all the data you can get. And then a motion management that is advanced and not just I'm waiting for a resting phase, and then ready for clinical testing. And then obviously that could be a bit more flexible and modular, so you can exchange some of these building blocks and get different acquisitions and contrasts. So this is a simplified schematic on what the free running framework is. You have a 3D radial acquisition in K-space, and then several post-processing steps that extract the physiological motion. And then a compressed sensing reconstruction that tries to make use of all the data in different different physiological phases. For interest of this presentation, I will focus on the three main pillars of this free running framework, which is the acquisition, the self-gating part, so the extraction of the physiology, and then the reconstruction. So as for acquisition, in theory, this framework is quite flexible as long as your trajectory is uniform through time. But what we use is usually a 3D radial acquisition with this phyllotaxis pattern, which basically means that you acquire spiral of radial readouts for every shot, let's call it. And this rotates with the golden angle, so that any subset of this trajectory you take has a certain kind of spatial uniformity. And as you can see in this slide, the first readout of each of these interleaves is always the same, and we use that for navigation. And this is the paper of the trajectory. So this was the navigator setup, as I showed before. And the difference, so the first step we did was changing the building block of the sequence. So it's still triggered at the beginning, but we shifted the navigator through from being an external navigator to part of the data acquisition. And that is going to be this one, the readout that I showed you that was acquired at the beginning of each interleaf. And then you can try to track the blood pool motion directly instead of the lever. And then you can actually use all the data you acquire because you are now tracking the organ you are acquiring and not something else. And this has a predictable scan time because you use 100% of the data. And this kind of acquisition was introduced by Christian Stenning with Matthias back in, 2005. And then we use a slightly different version of it that was developed in Erlangen. And what happened in Lausanne at the beginning was that, okay, this worked at the scanner, which was obviously something very appealing for the clinicians. So both acquisition and reconstruction were fully implemented at the scanner. And so we tried to insert it in the clinical protocol in a place where they would not do anything otherwise. And this was very successful over time. This is an old slide that stops at 2016, but in something like 4 years, they acquired 3,000 data sets with this sequence. And this actually got a lot of clinical publications, not only from Lausanne, starting from a radiology paper to different institutions that were using this sequence, because as I am a Siemens employee, this sequence could be deployed as a work in progress package that can be distributed to other Siemens collaborators or customers, and they can make their own clinical studies with it. So this is just to show the power of having something that works at the scanner completely. And this is not only for clinical publications, that there were a lot of spin-offs, let's say, of this sequence with different motion corrections, different contrasts, and mainly from our group. So this was also something that helped a lot of PhD students for their work. Now we go to the actual free running part. So from this triggered sequence, in which we still have to take care of having a resting phase of the heart, so we always acquire the same phase. The first step was simply to take out the TCG triggering and do the same building block but continuously. So we took out the T2 prep because it's a lot of energy deposition, but then the block is the same, so fat saturation, then this navigating readout and the data acquisition, and we just acquired continuously over the whole cardiac cycle. And then now you have both cardiac and respiratory motion that are encoded into this 1D projection that you're acquiring regularly. Before it was only the respiration because you were assuming that you had no cardiac motion. So what we do after that is basically taking the different cardiac phases, so the different interleaves, and then aligning them into the same cardiac phase so that you could retrospectively reconstruct one single heartbeat. And this is the concept of how we do the reconstruction. And the idea was published at the same year, basically between from us and a group in LA, so from Jeanning and Simone. And this is the idea of having this 3D radial acquisition continuously running. And then obviously you can look at one single image or a 3D scene reconstruction. But this is then the second step. And the second version that we have now, we try to remove the fat saturation because the fat saturation doesn't behave as you would like to because there is no recovery time. So we try to encode the fat saturation capabilities in the sequence, being it a different pulse, like yesterday Xavier was showing, or being, I don't know, Dixon approach or something like that. But then the acquisition block becomes very simple. It's just data acquisition. So there is no pauses for doing preparatory pulses, at least in the basic sequence. And then the concept is the same. You have both motion encoded, and then in the reconstruction, you try to align everything to have a consistent cardiac phase and respiratory phase. And here brings to the self-gating part. So you have now all this data that you acquired over several minutes, but they come from completely different physiological states. So you have to sort them according to similarities of this data because they come from end expiration or a particular cardiac phase. So what you do, and this slide is from Lorenzo, is take, well, in this case, the center of the K-space center, but you can take this superior inferior projection. you look at the frequency content of the, is it okay? Yes. Of the frequency content of this series of SI projections. And then what you should see is that besides some trajectory related frequencies, there are two peaks, one that is at the respiratory frequency and the other that is at the cardiac frequency. And then you try to extract the part of the signal or the principal components of the signal that have the most energy in these two frequencies, so that you can end up with two different signals, one that represents respiration, maybe a point there, whatever, one that represents respiration and the other that represents the cardiac motion. And then you can start sorting your data. The first self-gating paper that I know of is from Andrew Larson, in which he demonstrated that from the center of K-space, you can the trajectory would encode motion and you can extract the cardiac motion from it. And the way we are doing it is now described in the paper of Lorenzo from MRM. The third part is the reconstruction, which our moderator is the master of. And it's basically what happens is now you have your acquisition, you have your physiological signals that you extracted, and what you have to do is to sort your bulk of data into these different phases so that you can create some temporal dimensions in which your image is redundant. So it's the same anatomy, but in different phases. And then you can use this redundant information to do a comprehensive reconstruction. So basically what happens is you have this, 120,000 lines of K-space, and you have to sort them between among different cardiac and respiratory phases, put everything in this comprehensive framework. And from an image that would look something like this, if reconstructed without any sort of regularization, you end up something that has much more signal and less noise. Yeah, this one. And the first idea of using physiology as a temporal dimension came from NYU, from Li Feng, with this XT-GRASS paper that then we extended. And indeed, with them, we have the first 5D or large sparse MRI, so the first trial of this, combining the idea of Simone of having this continuous acquisition 3D radial with this reconstruction. And then again, once you manage to sort the data and reconstruct them, you can just visualize what you want. So you can easily visualize, for instance, the respiratory motion. So you block one of the cardiac phases and then just display the different respiratory phases one after the other. So you can see that the motion is resolved. Or you just freeze one of the respiratory phases and then look at the cardiac motion there. Or you just choose one of the volumes and go through it to see the anatomy. So for instance, you choose the resting phase in diastole and then try to see where the coronaries go. And this is our first experiences in Lausanne. These are actually data sets acquired by Jerome. So this was the second version of the sequence. There is no fat saturation, but this was to have a 3D sequence. So the idea of this was to have a 3D cine sequence without any sort of gating or triggering and see how much we could push the resolution and how much the acquisition time would go up or down. So the 1 millimeter acquisition is about 8 minutes, but then you can, if you go down to 2 millimeters, you can acquire a whole data set in 2.5 minutes, free breathing, and it looks still pretty decent, I would have to say. And in comparison, the whole breath holding cine part of the protocol that you saw at the beginning, because you have to allow the patient to recover, it's about 12 to 15 minutes. So, and with the pretty much 2 millimeter resolution, so we are going down of a factor of 10. And these are some data sets from patients from another site. So this is the Children's Hospital in Philadelphia. They use ferumoxytol as a contrast agent in pediatric patients, which is ideal for our sequence because then you don't need to do fat saturation because the signal of the blood is so bright, and then we can just acquire a GRE sequence. And this is also an example on how the fact that everything is implemented in a user-friendly way, then you can have very fruitful collaborations with other sites. We do this now recently since like a couple of years also at the SHU. So in the pediatric patients or in the congenital cases, they actually inject ferumoxytol from time to time. It's an iron-based contrast agent. And these are reconstructions of patients from the SHU. The other question is, okay, now what changed from the slide I showed you at the beginning is that now it's not, everything is not at the scanner anymore, because yes, the acquisition is much simpler. You just place a field of view, click start, and then acquire some 10, 12 gigabytes of data, but you have to take them from the scanner and reconstruct them somewhere else. So this is much more powerful than before, but took away the fact that you get an image at the scanner, which was appealing for the clinicians to actually run the sequence. So one of the questions we asked is that, can we have everything? So can we also have some fast reconstruction at the scanner before? And this is the idea behind Simba. So these slides were given to me by Ludovica. And the idea is that you have this free-running acquisition, as I showed you before. You have these superior inferior projections that you use to extract physiology. But what if you don't want to extract physiology? What if you want to just see within your data which ones you can put together, like which ones are the most similar data points you already have, and maybe you have enough for a static reconstruction. So regardless of physiology, we try to project these superior inferior projections in a space that has less dimensions than pixels times coils. And then we try to see how the pixel, how the data points group in this space. And the idea is the closer they are in this reduced dimensionality space, the most similar the data points are. So we can cluster them together and then choose a cluster that is compact enough and has enough data, and then just do a grading reconstruction at the scanner. This takes pretty much like 2 seconds more than the actual grading. And you get, in theory, a static image at the scanner. This was originally the work of John that was published in MRM. And now the idea is, can we have everything indeed? So you have this free running acquisition, which means you have a cubic field of view. You place it around the heart and click start. Nothing has to be done, no 350 clicks. The sequence runs for, let's say, 6 to 8 minutes. And then at the scanner, you can get a similarity-based reconstruction. So as we said, we cluster this data. If you were to reconstruct everything together, you would get a very blurred image because you have all the respiratory phases, all cardiac phases together. But then you just tell the reconstructor to just reconstruct a subset of the data that you cleverly select, and you get a much sharper image at the scanner that actually the clinicians can use to see if the acquisition went well, which is more important than one would think. And then they can even use it to plan different scans, like, for example, flow. And then with the same data, you can take the raw data and then go and do your more complex but more fruitful reconstruction and have this 3D cine reconstruction, let's say the day after for the moment. And to show you an example, so we can add different kind of corrections and denoising to this Simba. So this is a data set from Oxidol data set, how it looks uncorrected. So all the data together. This is Simba, so more noisy, but much sharper because it's one single phase. And then you can add some denoising and some of this XD reconstruction, so using different clusters. And then you can have very beautiful images, actually. This is a comparison of this data set versus the same patient acquired with CTA. And actually, you see that there is a stent in the pulmonary artery, which the CT doesn't like very much. But in DMR, you just see this black signal, and the anatomy is very similar to the CT in this case. So you can see the coronary format. How can I stop the automatic? Okay. So now this is the cardiac MR examination as the standard approach. This is what we did at the beginning. So substitute the waiting time with the 3D self-gated. But what if we think a bit more out of the box? Now this is the blocks we really need because it's perfusion and NLG, they require contrast. What if we don't want even the localizers and we just do this ND anatomy and function? So you get a localizer because the reconstruction of the static image goes at the scanner, and then you would have the cine to reconstruct afterwards, and then just perfusion and LG, and then you still have the waiting time in which you could do, for instance, another 3D free running that could be flow or mapping. And why not then ND perfusion if we manage to get it there, and then you would have a protocol that is really 3 clicks instead of 350. And where you have all the information you need. And this is obviously made possible by the collaborators at the SHUV, but also by a large network of collaborators that actually try our sequences locally. And with this, I would like to thank the whole team in Lausanne and also the clinicians that actually